Hello, everyone. I'm Xiangyu from Princeton University, and I'm going to give a talk on a proactive ML approach for detecting backdoor point samples. This is a joint work with Tinghao, Jiachen, Wang, Tong, Saeed, Mahloujifar, and Prateek Mittal at Princeton. So let's start by imagining an ideal world for machine learning. So where we have a training data set that contains clean features that we are really interested in. And then let's say we are doing supervised learning, so we also have correct annotations of these features. And if we train a model on such an ideally clean data set, we can expect that we can get a clean model that learns the correlation between its clean features and their correct annotations, right? However, in the reality, we have to face with the existence of attackers. So you can imagine like there may be an attacker that can manipulate some data in a data set by injecting like some spurious features that we're not really interested in into our samples. For example, it can be a patch pattern. It can also be superimposed sine signal. It can also be even geometric deformation on the shape. And there are a lot of such kind of manipulations. And then the attacker may further associate this data with some targeted annotations. For example, just a specific target class. And in the literature of adversarial machine learning, we call this kind of data manipulation attack as backdoor poisoning attack. And those manipulated samples are called backdoor point samples. And those spurious features injected by the attacker are usually referred to as backdoor trigger. And if we have a lot of such kind of samples in a data set, they essentially, and all of them contain certain backdoor trigger and are all labeled to a target class, then they essentially establish a spurious correlation between the trigger and the target class. Well, in a data set, if some of our samples are replaced with such kind of backdoor point samples, we call it a poison data set in the literature. And basically, in a poison data set, it will contain both clean samples that encode the benign correlation between clean features and their real semantics, and also the backdoor point samples that encode the spurious correlations between the backdoor trigger and the target class. And if you train a model on such kind of poison data set, empirically we find that at the end of the day, we will get the backdoor model that picks both the benign correlation and the backdoor correlation, like the spurious correlation between the backdoor trigger and the target class. It's called backdoor poison attacks. And as a result, in a backdoor model, we'll find that the model will have very high clean accuracy on normal test data because it does pick up the benign correlations, right? On the other hand, we find that as long as the backdoor trigger is present in the test sample, the model will have high propensity to predict samples to a target class assigned by an attacker. And it will completely ignore the real semantic features. And we call this kind of behavior controlled by the trigger as a backdoor. In our work, we look into the problem of detecting and eliminating backdoor point samples. To clarify, let's consider the threat model as follows. We assume that attacker will give the defender a poison data set with both clean samples and some backdoor point samples. And we want to know whether the defender can identify point sample and eliminate them from the data set. So how can we do this? In the existing literature, we look into some prior arts. And we find that surprisingly a lot of work are built upon a post-hoc workflow. And in our work, we summarize it in an abstract framework. Basically, in this post-hoc workflow, the attacker will give the defender a poison data set. And the defender will first allow the backdoor poison attack just to proceed as per the adversary's expectation by just routinely training a backdoor model on this poison data set without any defense. And then the defender usually will presume some characteristics of the backdoor model. So they basically just use some assumed characteristic function to project every sample in the poison data set into a characteristic vector in a characteristic space. And then they further design decision function on the characteristic space of these vectors. And a sample from the data set is identified as poison if and only if the decision function gives out a positive indication. Maybe this sounds a little bit abstract. Let me give you a concrete example, which we refer to as latent separation-based poison detection. We find a lot of prior work all built up on this kind of framework. Basically, they give a poison data set, the defender will just train a backdoor model routinely on this Poisson dataset. And then they will project the Poisson dataset into the latent representation space of the backdoor model. And then they just perform another clustering analysis on these samples. Empirically, we often find that the Poisson sample and clean sample will form two separate clusters. So the defender can easily identify those Poisson samples by performing some clustering analysis and just eliminate all the abnormal cluster. And indeed, latent separation is quite pervasive among multiple attacks. Like we experiment with 10, 11, even 11 attacks, we consistently observe this kind of latent separation. That justifies why this kind of post-hoc approach is quite popular. But in this work, we want to highlight that there is one very important, very severe limitation in this kind of post-hoc workflow. That is the post-hoc signature or characteristic of this backdoor model are not controlled by the defender. If we build our defense on this kind of post-hoc signature, we usually will find that there will be a lot of failure cases. For example, when the Poisson rate is low, that means only a very small portion of training samples are Poisson samples. We find the model trained on this dataset can still be backdoor, but the latent separation is no longer observed. If you build your defense based upon this latent separation, you may probably fail. And also, adaptive attacks are also observed recently. Like if the attackers know the defender will build upon their defense upon some post-hoc signatures, they may just adaptively design defenses to avoid leaving this signature in the backdoor model. Based on this limitation, in our work, we propose a proactive mindset to mitigate this limitation. The idea is, as opposed to a post-hoc workflow, that just passively train a backdoor model routinely on the Poisson dataset, and hopefully that they have some distinguishable behaviors on Poisson and clean samples, so we can use them to detect Poisson samples. We propose that maybe we can proactively derive an inference model on the Poisson dataset that will exhibit certain distinguishable behaviors on Poisson and clean sample by the design of the inference model. So how can we do this? In our work, we propose a concrete illustration of this mindset. We call it confusion training. Let's say we start from a Poisson dataset, it contains the clean samples with the correct semantic label. We also have the trigger applied to the backdoor Poisson sample with a target label. We assume we have a very tiny clean set of clean samples. This tiny set is very small compared with the Poisson dataset. You can collect them manually. Maybe you can even take pictures with your own cameras. You may also use some algorithm like just now, the Ethan introduced their meta-save algorithm to save out some clean samples for this purpose. And then with these two samples, during training, we will sample data from both small data split. We call the regular batch when it is sampled from the Poisson dataset. Basically, it will contain both clean sample in the Poisson dataset and also contain a Poisson sample from the Poisson dataset. We call another batch as a confusion batch from sample from our clean set. It's a tiny clean set. And the point is, we always randomly label this clean sample in the confusion batch. And the effect will be that in this confusion batch, basically we decouple the benign correlation between the clean features and their semantic labels. And then we will train an inference model jointly on regular batch and a confusion batch. We will assign a very large weight to a confusion batch. And in this way, the confusion batch just acts as another Poisson samples. They will exhibit a strong disruption on the learning of benign correlation because they just randomly label those some benign samples. And on the other hand, in the regular batch, we still have some Poisson samples that associate the backdoor trigger and the target class. So the spurious correlation between the backdoor trigger and the target class still remains intact. So at the end of the day, if we do joint training on the regular batch and confusion batch in such a way, we will find that the inference model will fail to feed those clean sample because of the disruption from the confusion batch. On the other hand, the model can still correctly feed those backdoor Poisson samples. So there is a simple way to distinguish between these two types of sample because we can just identify all the samples that are correctly fitted as backdoor point samples. Yeah, that's the idea. To evaluate the confusion training, we first look into how well the method can be used for point detection. We consider two metrics: the true positive rate, basically the ratio of backdoor point samples that are detected, and also the false positive rate, the ratio of clean samples that are mistakenly identified as poison. To make a very strong evaluation, we actually do a very large benchmark evaluation. We consider 11 types of attack on CFR10. This includes some known hard example like the clean label attack. We use CL to denote that. Also like the WANET, ISSBA, and also two adaptive attack we mentioned before. And also we consider 9 types of attack on GTSRB. It's very interesting to see that we find the confusion training is quite effective and robust. We consistently achieve over 94% true positive rate in all cases. And also we, in the worst case, we find that also the false positive rate is bounded within 3.5%. And also to show the advantage of our approach, we compare with 7 other poison detection approaches. We find that only our approach can consistently achieve a high TPR in all cases. And you can see in other cases, indicated by the red block, they will suffer from some failure cases. And also we evaluate confusion training. We investigate whether confusion training can mitigate backdoor poisoning attack. That is to say, after cleaning the data set, we retrain a model on the cleansed data set. We say whether the model will still be backdoor. We measure clean accuracy and attack success rate. The clean accuracy denotes accuracy on clean test set. The attack success rate denotes the ratio of trigger planted tested backdoor sample that are misclassified to a target class. We find that our approach is similarly effective. Like after using our poison detection and eliminate all poison samples, we can successfully mitigate backdoor attacks in all cases. The attack success rate are controlled under 4% in all cases. And also, we still have achieved high clean accuracy on CFR10, it's over 92% in all cases, and also on high accuracy on GTSRB, over 96% in all cases. And this is really a large table. We compare with 11 backdoor defenses in the literature, like to show whether our approach can be better. We find that CT is the only approach that consistently reduces attack success rate below 20%. And in other cases, indicate by the red block, we can say this approach, although the approach effective in some cases, they may fail in other cases. That means CT is indeed more robust. Also, we consider the scalability of our approach. We perform, we use a full ImageNet and simulate 3 backdoor poisoning attack to find that our approach can still be effective in the ImageNet scale with 99% of true positive rate of detection. Actually, it's almost 100%. And also, you can achieve nearly 0% false positive rate. And also, we find that confusion training can also be applied beyond the image domain. We take the poisoned malware classification data set as an example, which is Amber. We're doing some poison on Amber. We find that we can also achieve nearly 100% true positive rate and less than 4% false positive rate in terms of point detection. So finally, I want to summarize in 4 points. First, we uncover a post-hoc workflow underlying the many prior backdoor point sample detection, and we also reveal their limitations. We also suggest a proactive mindset to enlighten the design of better approaches, and specifically, we propose confusion training as a concrete example of the proactive detection. Finally, we do a large benchmark evaluation showing the effectiveness of confusion training and also show its scalability to large data set and also generalization beyond computer vision. And our paper is awarded with artifacts reproducible, so it's public. Yes, thanks. Do you have any questions?